All right, section 15.2, we're going to talk about heterogeneous equilibrium. And remember, we kind of previewed what happens if something happens in about 2 steps or more than 2 steps. Well, a couple things here. The concentrations of solids and liquids are essentially constant. Rarely are you going to see the concentrations of solids and liquids change in solution. So what that means is when you have a solid or liquid in an equation, you are not, and let me repeat, you're not going to express that in the equilibrium equation. So you are not going to express a solid or a liquid in a equilibrium equation. So below we have lead chloride, lead 2 chloride, breaking down in solution into 2 ions. We put the ions in the solution or in the equation because they're the aqueous state, but we do not put the solid because the concentration of solids and liquids rarely change. So here's just an example. We have calcium carbonate breaking down into carbon dioxide and calcium oxide. Since we have 2 solids and 1 gas, as long as the solids remain somewhat, the concentration of carbon dioxide will remain the same as well. So just a heads up there, we don't put solids or liquids in the equilibrium constant. So when we do equilibrium calculations, what's it look like? Well, we're going to start doing these complex problems, and they're going to look something like this. It's going to give you a lot of information. It's going to give you a specific temperature, and we're going to have to figure it out. Now we are going to call these equilibrium problems ice problems. And in a second, you're going to see why we call them ice problems. So a closed system initially contains 1.000 times 10 to the negative third molarity H2 and 2.00 times 10 to the negative third molarity I2 at 448 degrees Celsius, and it's allowed to reach equilibrium. Analysis of the equilibrium mixture shows that the concentration of HI is 1.87 times 10 to the negative third. Calculate Kc at 448 degrees Celsius for the reaction taking place, which they show you below. Now, why do we call it an ice problem? Because we have an initial, we have a change, and we have an equilibrium. So we have I, C, E. Now, what do we know initially? Well, it tells us the starting points of the initial concentrations of both our reactants. We were told that the initial concentration of H2 is 1.0 times 10 to the negative third, and of I2, 2.0 times 10 to the negative third. Now, since this is initial, our concentration is 0 for HI. Our initial concentration is 0. What that also tells us is that at equilibrium, our concentration of HI was 1.87 times 10 to the negative third. So that is what we know. We have to figure out how to fill in the other 5 boxes to figure out Kc, or the equilibrium constant. So, well, we know that if our equilibrium for HI is 1.87 times 10 to the negative third, the change is going to be 1.87 times 10 to the negative third. Now, using molarity, or not molarity, using stoichiometry, if we go back here, remember we have 2 moles of HI and 1 mole of each. So using stoichiometry, we can take that 1.87 times 10 to the negative third and divide it by 2 moles, because we have 2 moles of HI and 1 mole each of H2 and I2. So when we take 1.87 times 10 to the negative third and divide it by 2, it tells us that the change for both H2 and I2 was 9.35 times 10 to the negative fourth. That is how much it's losing. So our reactants are losing concentration, our products are gaining concentration. Well, now that we've calculated our change for all 3 of these, we can go ahead and calculate our equilibrium by simply subtracting. And when we subtract, we can figure out that at equilibrium, our concentrations are the following. For H2, it was 6.5 times 10 to the negative fifth, and we took initial minus change to get that. At equilibrium, I2 was 1.065 times 10 to the negative third. We took initial minus change to solve for that. And we knew that the problem told us at equilibrium, the concentration of HI was 1.87 times 10 to the negative 3. So we can take all three of those values at equilibrium, we can plug them in, and we could solve for Kc hypothetically. So that is what we're going to start doing, is we're going to start focusing on these ICE problems, initial, change, and equilibrium. And we're going to spend a lot of time working on these ICE problems. Last thing, after the introduction to an ICE problem, we're going to talk about Q. Q is the same ratio as Kc, the equilibrium constant, but that's for a system that's not at equilibrium. So we use Kc when we are at equilibrium. We use Q when we're not at equilibrium. So to calculate Q, we substitute the initial concentrations of the reactant and products into the equilibrium expression. So for Q, we're going to use the initial concentration. So Q, all a Q is that Q is when our system is not at equilibrium and we're using the initial concentration. A couple things with Q to wrap up 15.2. If Q equals K, the system is at equilibrium. If Q is greater than K, there's too much product and the equilibrium will shift back to the left as it starts to form more of the reactants hypothetically. And if Q is less than K, we have too much reactants and the reaction will shift back to the right. So if Q, let's talk about that one more time. If Q equals K, our system's at equilibrium. If Q is greater than K, there's too much product, so it's going to start to form more reactants to achieve equilibrium again. All right, so if Q is greater than K, we have too much product, so we're going to start to form more reactants. And the exact opposite is if Q is less than K. We have too much reactants, so we're going to form more products, so our equilibrium will shift to the right. So a little bit of Q and K and the similarities between Q and K. Remember, K is our equilibrium constant. Q is assuming we don't have equilibrium. So we're calculating our concentrations not on equilibrium. So that concludes section 15.2. Key things in 15.2. We don't use solids or liquids in our Kc equation. We are starting to study ICE problems and the differences between K and Q. And that concludes section 15.2.